So this is lecture number 13, and in the last lecture we basically studied how to derive the solution of a non-homogeneous of a homogeneous state space model. A homogeneous state space model basically refers to a state equation input where our system is unforced. That means our input is basically zero. Now we'll basically be seeing the solution of a non-homogeneous state equations. So in case of a homogeneous state equations, xt is equal to phi of t into x naught, where phi of t is basically your Laplace inverse of SMIC inverse known as the state transition matrix. The state transition matrix basically implies a system or a matrix that will transform your initial states, that will transform your states of a system from their initial time to their final time. Now in this case, u will not be equal to 0. That means we'll be having the equation x dot equal to ax plus bu. Fine. These are all in t domain. So as we did the last time in the alternate case, t multiply both sides by phi of minus t. That means phi minus t into x dot t is equal to pi minus t into a xt plus phi minus t b u of t. And if we take this term on the left hand side, phi of minus t x dot t minus phi of minus t a x t is equal to phi minus t b u of t. So this is nothing but d by dt of phi of minus t xt, जैसे last time किया था, is equal to phi minus t b u t. Fine. Now instead of writing t, what I will do is I will transform t की जगह में tau लिख दूंगा. So this means d by d tau phi of minus t phi of minus tau into x tau is equal to pi minus tau b u tau. Fine. So I have basically transformed the variable t to tau. Now integrating both sides, d by d tau of phi of minus tau x tau, d tau integral on the right hand side 0 to t phi of minus tau b u tau d tau. Fine. Which implies d tau इस साइड से कैंसिल हो गया. So applying the limits, this is pi of minus t into xt minus pi of 0 x0. Upper limits and then lower limits ऐसे ही is equal to 0 to t pi of minus tau b u tau d tau. Right? So ये जो right hand side है we cannot integrate this because we do not on the left hand side d and d tau simply got cancelled. The integral and the differential basically got cancelled. But on the right hand side there is no such provision, so it will remain as such. So therefore phi of minus t xt minus is equal to pi of 0 x0 plus 0 to t pi of minus tau b u tau d tau. एंड इसके बाद हमने क्या किया था लास्ट टाइम? प्री मल्टीप्लाई बोथ साइड्स बाय फाई टी. Multiplying by phi of t into phi of minus t is nothing but phi t inverse actually. We already know the properties of state transfer matrix. Into xt is equal to phi t into phi of 0 is what? Identity matrix into x0 plus phi t 0 to t phi of minus tau b u tau d tau. Fine. So phi of t into phi t inverse is actually identity matrix. Into x of t remains वहाँ पे खाली एक्स टी रहेगा. सो दिस इज एक्स ऑफ टी इज इक्वल टू phi t x नॉट. तो यहाँ तक तो ये सोल्यूशन सेम है. दैट वाज इन द केस ऑफ अ होमोजीनियस सोल्यूशन. अब इन केस ऑफ अ नॉन होमोजीनियस सोल्यूशन this term is additional, that is okay. So x of t is equal to phi t x0. This is the solution of a homogeneous state equation. Now in case of a non-homogeneous equation, this integral term is extra. Phi of t we can take inside. Phi of t into phi of minus t, phi of t1 into phi of t2 becomes phi of t1 minus t2. That is phi t minus tau b u of tau d tau. So this is basically the solution of the state equations that are actually represent the equation that actually represent non-homogeneous state equations. Fine. यहाँ पे आपका system it is stimulated by an external input. It's forced by an external input u. Right? In case of a homogeneous solution, x of t is equal to phi t x0. In case of a non-homogeneous state equation, xt is equal to phi t x naught plus integral term phi t minus tau bu tau d tau. Right? So this is the solution of state space equations. Now moving on, we have to do the analysis of state space models. So there are three important properties that we can basically determine using a state space model. One is controllability, second is observability. These two properties cannot be determined in case of a transfer function. We cannot determine these. We cannot determine whether a system is controllable or whether a system is observable using a transfer function model of a system. But using a state space model, we can say whether a system is controllable and whether it is observable And the third property that we can determine using the state space model is the property of stability. That can be done using transfer function approach as well. But in case of state space models, it is much more insightful. So, first property, that is controllability. So, controllability basically simply means, uh, in simplest terms, I can say if a system can be controlled or cannot be controlled, that basically determines the property of controllability. So if you are able to control the output of any system, the system is said to be controllable. If you are if you are able to control the output as well as the states of a system, the system is said to be controllable. If you are not able to control the output and the states of a system, the system is said to be uncontrollable. Fine. Uh, in uh, the proper definition of controllability is however written as, if you take an input of a system and you can basically shift that input value, you can transfer the input value from its desired initial states to the desired final states, then the system is said to be controllable. Fine. So if an input to a system can be found that will transfer the state variables, that will transfer the state variables of a system, state variables, that's basically xt of a system from their initial states to desired final states, then the system is said to be controllable. So if there exists any input, fine, there's, you have a system, you're applying an input to the system. Not apart from the output, now we also know there are some other states of the system, x1, x2, up to xn. So if you are able to transfer all of these states from their initial value to the desired final value in a finite amount of time, then the system is said to be controllable. If you are not able to do so, if you are not able to transfer the states of a system from their initial value to their final value, then the system is said to be uncontrollable. Being more precise, if all states can be transferred, it is known as fully controllable. If only some states can be transferred or controlled, whatever you want to say, from their initial value to their desired final values, then the system is said to be partially controllable. And if none of the states can be transferred, then the system is said to be uncontrollable. There are actually three Rather than just saying controllable and uncontrollable, we can also say if some of the states can be transferred while some other states cannot be transferred from their initial values to their desired final values, then the system is said to be partially controllable. If all the states can be transferred from their initial values to their final desired values, then the system is said to be fully controllable. And if none of the states can be transferred, the system is said to be uncontrollable. If you cannot control any of the states, it's an uncontrollable system. If you are able to control all the states, it's a controllable system. So this is about the definition of controllability. Now, how we can basically determine controllability? Right? So there is a system can be controllable, and if it has this property, the property itself is known as controllability. So determining how to determine controllability, whether a system is controllable or not. If the system has this property of controllability or not. For that, we basically find out a matrix that is known as controllable matrix. We define the controllable matrix MC is equal to B AB A square B. So if you have any state space model x dot equal to AX plus BU that is given to you, you know the value of A, you know the value of B. So you can find out this controllability matrix B AB A square B up to A n minus 1 B, where n will be the order of the state space model. So if it's a 3, if the order of the state space model is 3, so you'll have B, AB up to A square B, fine. And if the determinant of this matrix is not 0, or in other words, you will say MC has full rank. MC having full rank means MC will have the rank equal to n. Fine. Or in other words, we can say if the determinant of this matrix is not equal to 0, then the system will be controllable. And if the determinant of this matrix will be 0, then the controllability matrix cannot have full rank. Therefore, the system will be uncontrollable. So this is about the property of controllability. We'll do the examples later. The second property that I just mentioned is observability. So what does controllability mean? You can control a state and bring it from its initial position or initial state to its final desired state. The system is said to be controllable. Now, as far as observability is concerned, this property basically will say whether a system is controllable, is observable or not. So by observable, we can also say whether it is measurable, or the estimate of this, it can be estimated. इसकी बहुत सारी terms है, whatever you want to, however you wish to define it, or it's quantifiable, extra, whether a system can be observed or its states can be the system states rather, they can be observed or they can be calculated or they can be measured, they can be estimated. Such a system will be known as observable system, and this property the system will be having, it will be known as observability. Fine. So if the states of a system can be estimated, or you can say observed, then the system is known as observable system. Fine. In a similar fashion, this can be if all the states, it will be known as fully observable. If some states can be observed, can be estimated, then it will be known as partially observable. If none of the states can be estimated, then it will be known as a non-observable or an unobservable system. Or uh, going into a more precise definition, if the initial state vector, that is basically x naught t, can be found. So if we can find the states of a system, and basically you will be requiring the knowledge of the input and that of the output. So if the initial state vector xt can be found from ut and yt uh, over a finite interval of time, uh, then the system is said to be observable. Right? So you have a system here, you are giving some input, you are giving some output. So if you have the knowledge of both the input as well as the output of the system, and from the knowledge of these two, you can basically say what the states of the system will be at that particular instant of time, then the system is said to be observable. And now how to determine observability? Now, how you can say basically whether a system is observable or not? For that you will basically find out an observable matrix. For finding out whether a system is controllable, you define a controllable matrix MC equal to B, AB, A square B up to A raised power n minus 1B. For finding out observability, you basically define a matrix, observable matrix, which will be given by C, CA square, C, CS, CA square up to C, A raised power n minus 1, where n will be the order of A matrix. So again, if m naught, the determinant of m naught is not equal to 0, then this is observable. If the determinant of m naught is equal to 0, that means the system does not have full rank and it is unobservable. Right? So this is about the properties of two important properties that can be determined using a state space model, the property of controllability and the property of observability. So controllability basically means whether you can transfer all the states of the system from their initial states to their final desired states. The system is said to be controllable. Observability basically implies if you are able to determine or estimate the values of the states from the known values of input and output, then the system is said to be observable. Now let's do an example on this. So say for example, determine whether the following system is controllable or not. So your system is given to you, x dot is equal to 2, 6, 3 minus 1, x plus 1 minus 2u. So you have to determine whether this system is controllable or not. For that, you will basically find out the controllability matrix given by B, A, B, where AB is basically, B is known to us, B is this matrix 1 minus 2. AB will be 2, 3, 6 minus 1 into 1 minus 2. That means 2 minus 6, that is minus 4. 6 plus 2 is 8, minus 4, 8. So MC is basically B, B is 1 and minus 2, AB is minus 4 and 8. Now we have to see whether the determinant of this matrix, what is the determinant of this matrix? That is 8 minus 16. So 8 minus 8, sorry, 8 minus 8, that's equal to 0. So the determinant of this matrix is 0. That means this is an uncontrollable system. Right? Determine if the following system is observable or not. System is given to you, x dot is equal to 0, 0, 4, 1, 0, minus 3, 0, 1, minus 2 times x1 plus x2 and x2, x1, x2, x3, 0, 0, 1 times u, and y is equal to 0, 5, 1 times x. So you have to find out whether this system is observable or not. For that, you will basically find out the observability matrix given by C, CA, CA square in this case. So you'll find out the value of CA. CA will be 0, 5, 1 into 0, 1, 0, 0, 0, 1. Minus 4 here, minus 4, minus 3, minus 2. So this will be 0, 0, it is minus 4, minus 3, 3. Right? In the similar fashion, CA square will be 0, 5, 1. So you can do this using your calculators. 0, 0, minus 4, 1, 0, minus 3, 0, 1, minus 2. First find out the square of this, then multiply it with 0, 5, 1. So we'll be basically getting minus 12, minus 13, minus 9. So the observability matrix therefore will be C is 0, 5, 1. Then C into A, minus 4, minus 3, 3. Then CA square, minus 12, minus 13, minus 9. So find out the determinant of this. You will see the determinant of this will be equal to 3 minus 344, which is not equal to 0. Therefore, the system is observable. Fine. So this is how you basically determine whether a system is or is not observable by finding out the controllability matrix and by finding out the observability matrix. The controllability matrix is given by B, A square B. Observability matrix is given by C square. One is a column, one is a row matrix and another one is a column matrix. You need to keep that thing in mind. If the determinant is not 0, that means the system has full rank, therefore the system is observable. If the determinant is 0, means the system does not have full rank. If you understand what the term rank means, then the system will either not or will not be controllable or observable. Fine. So that's it for today. If you have any questions.